Hello everyone, I am Engineer Richard De Jesus, an assistant professor from De La Salle University, and I'm here to present the Rapid Visual Survey created specifically for the CHeRiSH project. Have you ever thought about how safe your house is? Here's a self-check survey to know how your house will perform during an earthquake. The result will tell us whether our house is properly built and was constructed in accordance to correct construction practices and was designed in compliance with design codes. Take note of some of the questions being asked here. Question 2 asks about when was your house constructed. Question 4 asks about the shape of your house. And question 5 asks about whether your house has been modified. At the end of the survey, an assessment is offered about how our houses will perform during an earthquake. Additionally, a recommendation is offered to make our houses ready for an earthquake occurrence. So if you get a score of 11 to 12 points, it may imply that your house is safe for now. But for verification, you are still recommended to consult experts. If the score is from 8 to 10, from this survey, it basically implies that your house might require strengthening. So to confirm this, you will also have to seek consultation from experts. And when your score for your house is only from 0 to 7 points, then you have to be alarmed. You really need to see an expert soon so that strengthening recommendations and modifications can be made. Here's another example of a rapid visual survey. This rapid visual survey, or RVS, was applied to public schools in the country in a project that involves the University College of London, or UCL, De La Salle University, and Xavier University in Cagayan de Oro. DLSU and UCL are among the main collaborators of the CHeRiSH project. So what is a visual survey? A rapid visual survey, or RVS, is an affordable and a fast procedure in assessing the safety of a structure during a hazard event. It enables the classification of structure according to risk it may pose when subject to different hazards. So what's the objective of RVS? It aims to identify the primary structural load-resisting system of a structure. These are beams, columns, and slabs, and foundations. It also identifies building attributes that modify the expected performance of a structure along with non-structural components. So here's an example of a building attribute that affects a performance of a structure. That is the construction of a structure on a slope. Because the ground where the structure will stand on is not on flat, it is required that the structure be supported by poles or long columns, and fewer slabs will rest on ground and many will be suspended. Due to this layout and structural requirements, some columns will be sized larger than the others, and this results to varying stiffness in columns. Shorter and more stiff columns compared to long ones, the flexible ones, will attract more seismic forces and could fail during a seismic event. This attribute of a structure affects the performance and can only be identified once you have seen the structure on site. RVS is a tool that enables you to identify these attributes and lets you assign scores to these attributes to know how much compromise they will contribute to the structural integrity. RVS allows user to evaluate the needs of a structure for retrofitting, which is a performance improvement against certain hazards like earthquake. From the result of visual survey, one can develop a hazard mitigation program, create inventories of building to be used for monitoring, project impact, and conduct pre- and post-event loss assessment. One can also post a hazard evaluation and can develop a model for performance of structure in terms of vulnerability. CHeRiSH Rapid Visual Survey, like what you see on the slide right now, is a rapid visual survey catered specifically for cultural heritage structures. And this CHeRiSH RVS is the one that was used in conducting a rapid visual survey for CH structures in Calle Real, which was conducted in July 2019. So the CHeRiSH RVS has the following parts: general information, building information, roof information, structural information, masonry, and concrete or confined masonry. General information aims to identify and locate buildings, which is an important basic information. This can be achieved by providing the address and the location through GPS. Surroundings must also be described, such as nearby buildings, description of buildings adjacent to the structure being assessed, block shape and position on the block, and determining the time of construction. Some of this can be done before going on site. Construction year. The age of the building is tied to design and construction process or practices. By knowing when a building was constructed, one can tell the basis for the design of the structure. One can also identify the construction process during the time of construction. By knowing this crucial information, an expert can determine if a structure is adequately designed to withstand a particular hazard, such as earthquake. The demand from a structure for an earthquake, for a structure constructed before 1970, is different from a structure constructed recently. So, all structures must be evaluated based on the demands of loads, based on the current code. Block shape. This information confirms the address or location of the site. This also provides information that can support items in the latter portion of the RPS. For example, pounding due to adjacent buildings. You can use the following visual aids to answer this particular item in the RPS. So a block can look like a triangular shape, and if the structures on that block almost have the same age, then one can say the growth is synchronic, otherwise diachronic. So block can also shape like elongated one. So for this item, you will simply identify what the shape is. So it's triangular, bulk shape, elongated, and whether the growth is synchronic, diachronic. If the buildings are constructed individually and separately, then you can also identify that to be individual buildings or under classification number 7. So you can use the following visual aids to answer this particular item. So next is building information. This information requires simple building plan, number of stories, story height, spandrel, connection of exterior walls, wall openings, opening layout, plan irregularity, height irregularity. This part provides an overview of building configuration, like how tall the building is, how does the building look when viewed from above, is there a plan irregularity, etc. It also identifies building attributes which can be observed from the street that affects the performance of the building. For example, opening layout, facade irregularity, height irregularity. Simple building plan. Simple building plan could be a skillful sketch of a building or a simple floor plan drawing, but both shares an information that reveals some of the basic geometric features of the structure, which may have an influence on structural performance. Stories or story height. The number of stories or story height has to do with the height of the building, of course. Damage to a building is somewhat influenced by its height, and this information is a good indicator of a building's height. Spandrel. Spandrels are technically beams. In areas where there are openings, spandrels are the ones carrying the weight of walls above the openings. Without it, walls will have no support and could fall off. So how to detect? Find a portion of the masonry wall between openings, 2 vertical openings, and that one that connects 2 vertical piers, most likely that will be the spandrel. Walls, connections, openings. Connections of walls at the edges can be visually inspected on site if there are exposed areas to show this. Structural drawings, if available, has this information too. Wall opening dimensions can be measured on site. Opening layout. The structural performance of a building is influenced by stiffness or masses per floor. Openings like doors and windows provide a picture of how stiffness and masses vary per floor. This item requires that the opening layout be specified as either vertically aligned at center or at the edges or at both edges. So for this particular part of the survey, you will simply identify whether the opening is at the edges, at the center, or at both edges. So here is a visual aid that will also help in answering this item. Facade is the front face of a building. Facade is said to be regular if the spacing between windows and door openings are equally spaced apart. The piers. Piers are sections of walls between openings. Resist most horizontal earthquake forces. So it is important that this part be continuous as possible. Otherwise, stress concentrations will occur at changes in pier thickness. This assumes that the walls are designed to carry loads because there are walls that are constructed but not designed to perform or function structurally. So most of the walls that we have here in the country are designed to be non-structural type. Internal structural wall. If there are structural walls, then the largest distance in the x and y direction, please refer to the figure at the bottom right. So the largest distance along the direction of x and y will provide answer to this item in the RVS. This requires an actual measurement unless a plan or drawing is available for the structure being inspected. External walls run along the periphery of the structure, while internal walls, they normally set the partitions in a building. So this item requires the thickness of these two components. Note that walls can be best measured in openings. For example, doors. So when you open a door, a portion of the wall gets exposed and you can measure the thickness from there. In windows, walls can also be exposed in those areas. So you can also measure the thickness of the wall from windows, from openings. Structural walls. These are walls that are designed to carry loads. Example of which are load-bearing walls and shear walls. This item seeks to identify if there are vertical static load paths from an upper floor of the building that is interrupted by a diaphragm and does not have another structural wall immediately beneath it. So take a look at this figure. So when the vertical static load path from an upper floor of the building is interrupted by a diaphragm, see the picture on the left, and that does not have another structural wall immediately beneath it, as illustrated by the picture on the right, then you will have to answer this particular portion in the RVS. So you can refer to this visual aid to say whether the structural wall is continuous or not. For plan regularity, it refers to the symmetry of the building in plan view. So the picture that you see here at the bottom right is a plan view, are plan views of buildings with different shapes. One is shaped like an L, one is shaped like a T, and one is shaped like a cross. So this is how it looks like from a plan perspective. The symmetry relates to mass and stiffness distribution, and it can be measured by comparing the longest dimension, L max, and the shortest dimension, L min. If the ratio between L max and L min is less than or equal to 4, then we can say that the plan is regular. Otherwise, it is irregular. So a rectangular plan is regular, while a plan that looks like a C is partly regular, partly irregular. So we say medium. In answering this RVS item, we say medium. And if the structure is shaped like an L, then it's irregular. With respect to height regularity, similar to facade irregularity, there should be no disruption due to irregularity or discontinuity of vertical structure layout. This irregularity can be assessed based on elevation view of the building and consistency of mass and stiffness with height. To answer this portion in the RVS, you will just say either it's regular, medium, or irregular. Irregular is where story heights are uniform in a building. Medium is when story heights are different in buildings. The difference between floor heights is less than 0.5 meter or half a meter. But it will be considered irregular if the difference between floor heights exceeds 0.5 meters. The next portion of the survey has something to do with the roof. So roof information asks for roof type, slope, soffit width, mean roof height, the material for the trusses, panels, fastener, number of purlins, fasteners per purlin, the diameter of the fastener, and the amount of penetration, the connection between roof and wall, and the material used to connect the roof and walls, and lastly, ornaments if there's present in a structure. So it gives an overview of roof configuration. It identifies the material for roof components, and it also identify how roof is anchored or connected to the structure, especially to the structural components or members of the structure like beams and columns. The first item being asked in this portion is the roof type. So you will either answer this item as the roof being flat, as shown in this figure, or mono-pitch, meaning there's the angle, the inclination of the roof is only in one side. But if it is in several sides, then you say that the roof is multi-pitch. And then lastly, if it looks like this in figure 4, then you'll say gable. The type of roof is gable. So visual aids such as this can be used as a reference. This can be achieved, answering this item can be achieved if accessible by visual inspection. Otherwise, you may employ pictures taken by drones and then decide or judge from those pictures the type of roof that a structure has. Regarding slope, mean height, and soffit. So these are attributes of the roof. The first picture here at the bottom left describes what a roof slope is. So if there's a way to measure the height of the roof and then the horizontal dimension of the roof, then there's a mean to measure the slope of the roof. It is simply the angle between the inclined portion of the roof and the horizontal one. For the soffit width, so as given by this illustration, the soffit width starts from the wall up to the most exterior portion of the roof. Okay? And then for the mean roof height, it starts from the average grade of the ground up to the middle of the roof. So these two illustrations, if you have a pitch roof, this is how you measure the height of the roof. But if you have a flat roof, then the height of the roof will be from the average grade up to this line as described by this illustration. So this portion of the RVS can be answered using this visual aids. Now for the truss and purlin material, we have to know first what truss is. So for truss material, it can be either reinforced concrete slab, timber, or wood, or steel. So shown here in the picture is what truss is. And then those members running perpendicular to the trusses described by the blue lines are purlins. So similarly, you will also describe the materials used for purlins. The materials can be reinforced concrete, timber, or steel. Structural drawings may also have this information if they are available. In site inspection, you will need access to be able to identify or see these components. So often, one has to pick through the ceiling or attic to see these components. Without those access, you will have to refer to structural drawings to be able to identify the materials for these components. For the panel material, this item identifies the material used for roof panels, which can be timber or steel like GI sheets or others, because some uses solar panels for their roof while others uses clay tiles. Fasteners are tools that connects the components of roof. So GI sheets get connected to purlins by fasteners. So fasteners can be screws, they can also be nails. Inspecting this may require access to the roof. So it will be more convenient if plans are available, because you will simply have to check those materials from the plans. But when accessible, one can check the size of these fasteners, and you may be able to correlate the size with the depth of penetration that these fasteners go. So answering this particular portion of the RVS. For connection of roof to the wall, it describes the level of fixicity of roof to wall through the type of connection. Timber truss is usually pin connected. So if the truss used in a structure is made up of wood, then its connection will be described as pin connected or simply supported. So to determine the type of roof wall connection, you may use the visual aid as shown in this slide. So we already have mentioned about the simply supported one, and then the next one is pinned. So simply look for these materials and compare against this visual aid to identify the roof wall connection. Roof wall fasteners. This pertains to the material used to connect or fasten the roof to walls. To determine the material used, the following visual aid can be used. This can be inspected through attic or ceiling, but may require permission from the owner. So the difference of this from the previous item is that this identifies the material used to fasten the roof to the wall. The previous one identifies the type of connection, whether it's simply supported, pin connected, or fixed supported. So the material can be metal plate, as described here in picture 1, or single hurricane tie in number 2, or using nails, toenails, and then 4 is also a single hurricane tie. So you will simply have to check this particular item referring to these visual aids to identify the materials used in fastening the roof to the walls. And then lastly, for this section, the ornaments. Ornaments are typical for cultural heritage structures. This feature, however, poses risk because during an event, let's say an earthquake, these ornaments may fall and may may pose risk to um, a resident of the structure or to those that are nearby during an event to the structure. Therefore, it must also be given consideration for this particular item, the material being used, the type of ornament, and if possible, measure the size of the ornament will answer this portion of the survey. Again, accessibility could be a problem. It may be limited because, of course, it's located at the topmost part of the structure. So photos, drone shots can help in identifying the materials used and then perhaps provide an estimate of the size as well. So structural information, this aims to identify the structural system. The structural system which could be the lateral load resisting system and the material used for this. It also identifies the attributes that affect structural performance. Attributes such as the condition of the structure, the type of foundation being used, if there are diaphragms, and the way that these diaphragms transfer loads to adjacent beams, connection of parts, and vulnerabilities. It also aims to identify the changes made in the structure. Has the structure been modified? Has the structure been retrofitted? So this particular section will be aiming to answer those items. The first is the lateral load resisting system. So it will ask for the material used for this component. Materials in the primary load resisting system, they are designed to resist lateral loads. So by visual inspection, you can identify this. Materials could be reinforced concrete, masonry, timber, or steel. If available, architectural and structural drawings can tell what materials are used for this load resisting system. Or you can use this visual aid. For structural condition and environmental exposure. So, poor maintenance and deterioration of primary structural system can affect the structural integrity. Checking the structural condition of a structure can be performed by visual inspection. And if available, thermal scanners can help. Here's a visual aid. So this visual aid can help us assess this part. One can tell whether the deterioration can significantly affect the performance or it will only moderately affect the performance or will not affect the performance at all. Environmental exposure, on the other hand, can be assessed prior to conducting the actual site survey, as hazards can be identified through desktop survey. Nearby main water source can be identified. Distance from fault line can also be identified prior to on-site inspection. Foundations are structural members that transmit the loads carried by the structure to the ground where the structure sits. So depending on soil quality, foundations can be shallow or deep. This may not be visible on site, but if plans are available, one can tell the foundation type. Diaphragms can be identified through site inspection and similarly, if available, through plans. Load distribution concerns about how floor loads are distributed to the nearest or adjacent beam. Load can be directed in two directions. We also call it two-way slab, or through one direction only. So this can be determined by visual inspection if dimension length disparity is obvious, but a simple calculation can verify if slab is one-way or two-way. So take a measure of the dimension of the slab along the longer direction compared with the shorter direction. If the ratio between the longer direction and the shorter direction exceeds 2, then the slab is categorized as one way. And the manner that this type of slab distributes the load to the beam is through one direction only. Otherwise, two-way slab. Diaphragm wall connection checks about the quality of connection between floor and supporting load-bearing wall. You may use the following visual aid to answer this specific part of the survey. So connection can be simply supported. It can be by means of steel bars, or it could be by means of ring beams. Retrofitting. The repair or alteration to the structure to improve the response of a structure against lateral loads are referred to as retrofits. Visual inspection can check retrofits. Visual aid, as seen below, can help identify this. So, retrofitting can be through fiber reinforced polymer FRP, which is wrapped in columns as shown in this picture, or it can also be FRP but applied on beams. Another picture here shows FRP being applied on walls. Okay, so we may be able to use these visual aids to identify whether a retrofit is performed in the building or not. These are just examples. Modifications, unlike retrofits, these are addition to the structure, but it doesn't have the intention of improving the response of a structure against loads. In fact, many of these modifications even compromises the integrity of the structure. So these modifications can also be assessed by visual inspection, and we might be able to see some of this. So extension, opening on walls, addition of mezzanine, and addition of a floor or story. For vulnerabilities, these are considered to be the weak aspects of normal construction techniques that will compromise the integrity of the structure when subject to lateral forces. One can detect this from architectural or structural plans or by conducting visual inspection. Some of the vulnerabilities taken into consideration in this rapid visual survey are the following: a balcony, parapet. Parapet is a portion of exterior walls that extends above the roof. This can break during earthquake and may fall on the roof or onto the street. Gable walls are normally not braced, therefore vulnerable to out-of-plane failure. These walls provide support for the roof, and its failure can result in partial collapse of the structure. Mass irregularity. For example, if a particular story is being used for storage compared to other floors which doesn't have the same function. There's a difference in mass between that specific floor compared to others. So that is considered to be a vulnerability. And structures built on stilts. Additional vulnerabilities could come from roof thrust, as shown here in the picture above. Roof thrust happens when there's no roof tie beam. There's no beam that connects trusses. So without these tie beams, lateral loads are additionally applied to columns, and as a result of this thrust from the roof. Vault or arch is also a vulnerability, and so with the connections between orthogonal walls. If the connection is bad, then that's a vulnerability. Otherwise, the connection is okay. But there's a need for one to identify whether the connection is bad or good. Cracks. Cracks is a manifestation of an impending failure of a structure. So it is important also for us to identify this, including the locations. Cracks are more critical if the occurrence are along structural members. But if cracks are present along or on walls, and that particular wall doesn't function structurally, then it can be repaired. Another vulnerability is pounding. So buildings must have enough separation from each other, else they will strike against each other during earthquake due to swaying as a response of the structure to ground movement. Buildings that are adjacent to each other of varying heights can pound against each other during earthquakes. Pounding must also be considered if buildings are at the end of the block. For short columns. I hope that these pictures adequately describe what a short column is and how it responds during building shaking or earthquake. So column height can be shortened under several circumstances. So we may refer to the pictures being shown here to identify some of those circumstances. So during earthquake, when columns are short, it may fail by collapse. A while ago, we talked about construction on slope as one of the vulnerabilities of a structure, as one of the physical attributes that affects the performance of a structure. That's why we need to identify them. If we take a look at this picture at the bottom right, columns are of different heights because the structure is built on a slope. So one of the column being short, and it may fail because of the vulnerability associated with short columns. For this structure in B, there's an addition of mezzanine floor between these two columns. And because of that addition of mezzanine floor, the height of the column has been significantly reduced, therefore making the column short. So the failure of a short column is illustrated in this picture at the bottom left, referred as B. So during earthquake, during movement of the structure, short columns will fail by collapse. Now for strong beam, weak column vulnerability. Images on the left describes a structure with strong column, weak beam feature, and a structure with weak column, strong beam feature. Images on the right are computer simulations on how these structures will perform during ground shaking. Note that the structure with strong beam, weak column is vulnerable to collapse. How to detect this in structures? Simply compare the size of beams and columns as shown in the picture. When one floor is weaker, that means that floor is less stiff than others. It can be manifested by having fewer walls or columns compared to other floors. So that will be classified as a soft story. So we have here several pictures that describes a soft story. So what happens to buildings with soft story during earthquake? This picture at the right is a manifestation. It depicts the response of a structure with a soft story during movement in an event of an earthquake. Because top floors are heavier, it puts disproportionate lateral stress to the soft story below, causing a possible collapse. So these are actual buildings that collapse during earthquake because of soft story. And we don't have to go far, as one condominium building in Davao collapsed in October 2019 due to soft story as magnitude 6.5 earthquake hit the province. So I'm sure you have heard about this on the news. Another section is about masonry. It identifies the material used for masonry, such as masonry, mortar. It also identifies the condition of material used for masonry. So to be able to identify the condition, it checks for maintenance, water infiltration, mortar loss, improvements, and material testing conducted. It also establishes the degree of anchorage, the amount of connection of masonry to the building. Thus, it will ask about the connection quality and if there's a presence of wall ties. So masonry type. Masonry is the smallest individual component of a masonry wall. Here we aim to identify the material with which the masonry is made of. It can be a soft stone block, chaotic stone, regular sites stones, concrete blocks, or expanded clay blocks, among others. Typically in the country, we're using the concrete hollow block. But for cultural heritage structures, structures could be built made up of hollow bricks or solid bricks with lime and mortar, and then masonry with hewn blocks. So mortar will ask about what type of material is being used as mortar. So mortar is used to fill the gaps between bricks and blocks. It is a mixture typically of sand and a binder such as cement or lime, then added with water and is applied as paste, which then sets hard. So mortar can be cement, it can be mud, or it can be lime. Unless a maintenance record is available, maintenance can be judged by simply visually inspecting the target structure. One can judge easily if a structure is well maintained, not well maintained, deteriorated. So you can say maintenance is low, maintenance is medium, or maintenance is high for this particular item in the RVS. Water infiltration is the amount of water that sip through the building envelope to the interior of the building. So visual aids such as this can be used to identify and also the areas where water infiltration has occurred. So you might be able to observe painting or coating damage, water stains, loose cladding, rotting trim, falling debris, cracking or spalling, and efflorescence. The level of mortar degradation or amount of mortar lost since construction is asked in this particular item of the RVS. Through visual inspection, this can be answered. Mortar loss is low using this visual aid, while the second one is a manifestation of a medium mortar loss. The third one is high mortar loss. The transversal connection quality, including wall cores, masonry improvements, for masonry walls with multiple lifts, cavities, or infilled core or layer, the transversal connection quality refers to the connection between two leaves or two layers of the wall. So this can be through grouted steel pin, heather cores between the leaves, tie rod, or wall ties. And the last section is about concrete and confined masonry. Here it establishes the size of the structural members such as columns, beams, and the reinforcing bars used. It also identifies the material used for infill wall or mortar and then validates the size or dimension of the building by asking about the number of frames. But before we start with the components of this particular section of the RVS, let's differentiate concrete versus confined masonry first. Confined masonry is a construction system where the walls are built first and RC columns and beams are cast afterwards. While typical in our country is when RC frame is constructed first. So the columns and beams are constructed first before the walls are constructed. So typical components of a confined masonry building can be seen from this picture on the right. So there's a presence of toothing in wall, lintel band, sill band, RC vertical elements, and plinth band. For the number of frames, this is a structure that will be used for us to be able to define what a frame is. So under this section, the first item is about the number of frames. Simply count the number of frames during inspection. So for this particular example, we have 1, 2, 3, 4, 5, 6, 7 frames. Now for beams, columns, rebars, dimensions of beams, columns can be measured on site if plans are not available. To determine if rebars are corrugated or not, one can check with the structural drawing. Observing this on site may be difficult, so the size of the rebar can be checked from the structural drawing, but the presence of corrugation that will require physical inspection. It might be a little difficult to observe this on site unless the structure is heavily deteriorated, that a portion of rebars in some structural members are exposed already. So this is an example of corrugation in rebars. So the picture above shows a rebar that is smooth. So corrugation versus smooth. Regarding infill walls in mortar type, so infill wall in the country is typically a concrete hollow blocks wall. Though for cultural heritage structures, some may have used bricks or adobe, but these are typically considered to be non-structural. As differentiated a while ago, confined masonry versus RC frame with masonry infill, we can answer whether the structure is infilled or not. The material used for infill can be determined through inspection. Similar can be said about mortar type. So here is an example of a rapid visual survey for one of the structures in Calle Real. So the building is identified to be 1001. I have made a mistake here. This sample RVS is not for 1013, but for 1001 actually. So here's a summary of survey results. So all 25 structures in Calle Real were surveyed in July 2019 using the RVS, the CHeRiSH RVS. So from that survey, number of stories for the structure were identified. Regularity of plans were also identified. 71% of the structures are rectangular, while about 25% of the structures are L-shaped, and then there are 4% of the population that are C-shaped. In terms of structural condition, good structural condition has been observed for 60% of the structure, while 36% have manifested poor structural conditions. In terms of roof type, multi-pitch comprises 42% of the structure, while mono-pitch has been observed in some 10% of the structures. For vulnerabilities, pounding is the highest of them all, with 26% of the structures exhibiting pounding. And most of the structures have parapet also, 25% of them. Short column has been observed. Strong beam, weak column has also been observed in 4% of the structure. And then soft story, there's 1% of the structure had shown soft story vulnerabilities. So the collected data from RVS of all 25 structures in Calle Real were used to develop a prioritization index or indices, as summarized in the graph shown here. So these are the prioritization indices for all the 25 structures in Calle Real. Considering earthquake, this graph in the left, wind, and then the combination of wind and earthquake for this graph on the right. For seismic prioritization index, the figure shows a nearly similar baseline scores. This can be attributed to the similarity of some of the construction features of the structures in Calle Real. Most of them are reinforced concrete frame structures. All were constructed before 1970, while the code in the Philippines was instituted in the 70s. Common vulnerability factors such as pounding and degradation has also been observed. Only 4 assets fell below the 33rd percentile. Regarding the wind prioritization index, wind risk prioritization index has more variability than the seismic index. This is attributed to the variability of some of the construction features and degradation. Many has degraded roof as found in the survey. Structures with less maintenance or maintenance condition got a high prioritization index. Combining the result from seismic and wind leads to the development of the multi-hazard prioritization index. So this graph clearly shows that the wind hazard played a significant role in determining the prioritization scheme for CH structures in Calle Real. Observe the similarity between the two prioritization graphs. So, parehong behavior. Finally, considering the intangible value, such as local significance of a structure, the CH asset value of a structure, plus seismic and wind prioritization indices, we have here the graph for multi-hazard plus CH value index. It can be noted from this graph that one building stood out, Building 113, the Elizalde building, the COA building. It is one of the buildings that behaves better, yet it got the highest prioritization index. So this was attributed to the local significance of the structure being recognized at the national level. Hence, must be a priority. That's all for my presentation. I would like to thank everyone for your kind attention. Good day.